Alright, so this is problem 26.34, and it says that a light bulb A is marked as 25 watts, 120 volts. A light bulb B is marked as 100 watts, 120 volts. So this means that each light bulb has a respective power delivered to it when it's connected to a 120 volt source. Now A says, find the resistance of each light bulb. Now these are the two main equations we're going to be using to solve this problem, where here this is the power and we have I times delta V, and we know we can switch between I, delta V, and R using this equation here. So then we first kind of want to think about what's happening. If we have 25 watts, this is how much power our light bulb is getting. And when we compare that to 100 watts, obviously 25 is a lot less. This means this light bulb is going to be less bright. So the reason why you might want a less bright light bulb is, well, it's cheaper, right? And then 100 watts is brighter. Now, what does that mean in terms of the current? So here we have our little light bulbs. The more current we have flowing into our light bulb, the brighter it's going to be, because we have more charge going into it at each moment in time. So the more charge we have entering into our light bulb, the brighter it's going to be. So that means here, R of A is going to be larger than RB. The reason why I say that is because the stronger the resistance, we know the lower the current. So the more resistance we have here, the less current we are going to have flowing through our system. So that means that this resistor A, sorry, not resistor, well, it's a light bulb. This light bulb is going to have a resistance that's larger than this one here, because this one is pulling less current than this one. I'll rewrite that. So current of I is less than current of B. All right, so now we just need to figure out what is R. And we just have to use our two equations here. So we know P is equal to I delta V, and we know that we can replace I by delta V divided by R. So P is equal to delta V squared divided by R. And then all we have to do is say, well, that means R is equal to delta V squared divided by P. Resistance of light bulb 1 is going to be 120 volts squared divided by 25 watts. Resistance B is going to be 120 volts squared divided by 100, I believe it's 100 watts. We do the math and we see this is 576 ohms. This is 144 ohms. So just to re-emphasize this point, here, let's say light bulb A draws less current because it has a higher resistance and it consumes less energy. So that's why these numbers make sense. We're going to move on now to B, where B says, during what time interval does 1 coulomb pass into light bulb A? Now, 1 coulomb is the unit of charge. So we're talking about how much charge 1 coulomb enters into the light bulb. Now we know that the current is equal to, well, how much charge do we have per time? And we want to know how much time does it take. We also know from up here that we can express the current as P divided by delta V. So what we're going to do is say, well, delta T is equal to, and then Q delta V divided by P. So the amount of time it takes for 1 coulomb to pass into the light bulb is 1 coulomb times 120 volts divided by 25 watts. And that is going to be 4.8 seconds. Now C says, is this charge different upon its exit versus its entry into the light bulb? Explain. So what we're saying is, for C, we have our light bulb, and remember, the current before and after is the same. So we have the current everywhere is constant. But what happens is, let's say we have, this is our charge, it enters into our light bulb, and we have energy that gets transferred to the light bulb. And we're going to see that that's going to be in forms of heat and electromagnetic radiation. But there's still the same amount of charge that goes in and goes out. It just has less energy when it goes out and more energy when it went in. So there was more energy coming in, it loses energy, and then it leaves. But the amount of charge Q stays the same. So we have same Q going in as going out. And that is it for C. So we don't lose any charge. Now D says, in what time interval does 1 joule pass into a light bulb? This is essentially the exact same question as we had in B, but instead of talking about charge, we're going to talk about joules. Now we know that Q times delta V has the units of joules. So we're going to use this same equation here, but instead of being given Q, we're going to be given Q delta V. So that means delta T is equal to, well, what does it say it is? It says we have 1 joule divided by the power, 25 watts. So 1 divided by 25 is 0.04 seconds. So it takes 0.04 seconds for 1 joule to enter into our light bulb. Or pass into our light bulb. So then E says, by what mechanism does this energy enter and exit the light bulb? Now that's essentially what I said for C, where we have the same amount of charge going in as going out, but it loses energy. So here we have a drop in V. So we have a drop in the potential, which means we have a drop in the energy. And so the energy gets dissipated as, like I said, heat and also electromagnetic radiation, aka light. So it leaves in the form of heat and light. Now lastly, well, I think we have a few more. So we have F, which says, find the cost of running the light bulb A continuously for 30 days, assuming the electric company sells it at $0.11 per kilowatt. So we know how much watts, like the wattage that we're consuming, it's 25 watts. And we want to know, okay, well, we're going to run it for a whole month. How much is it going to cost us? So we know that the units of watts are joules per second. So that means we are consuming 25 joules per second. And we are going to be running it for 86,400 seconds per day. And then we're going to be running it for 30 days. So that's how many joules we're going to consume in our month. And that is going to be 64.8 times 10 to the 6 joules. Now, how much is it going to cost us? Well, we're given the cost. So we have 64.8 times 10 to the 6 joules. And we're being charged $0.11 per kilowatt hour. And we just need to translate that into joules. So we know that there are 1,000 per kilo. So to go from kilowatt to watt, we just have to multiply it by 1,000. And then we know that in 1 joule, the units are watt second. So we're just translating from one unit to the other. And then we also know that we have watts times hours, and we know that this is 360 seconds. So essentially what I did is I started off with, okay, well, this is how much energy that I'm consuming in the month. This is the price. Kilowatts, I'm going to try to get rid of that. So here I have the kilo part of the kilowatts. And then I'm also translating from watts to second to joules. So that here I have my joules and my joules. They cancel out there. Now I also have to be careful here because I'm told the price in kilowatt times hour. So, well, how many hour is in, so how many seconds are in hour? We have 3,600. So that is going to cancel out here. We're going to have this cancel out here. This cancel out here. Joules cancel here. Seconds cancel out here. Because the final thing we want is a price, right? So that's going to be $1.98. And that is our final answer.